Good evening and welcome everybody. It's Obi-Wan Pez for N Simplex Pachinko. We're going to be doing some mathy stuff tonight. And looking at what we have on the Cracking the GRE book. It's looking like tonight will be the revolutions of solids, at least for the first few questions. And then after that, we're going to have some stuff with limits and improper integrals. So we'll see how far we get. And thanks everybody for coming. Hi YouTube, those of you who are here. Always appreciate you all coming in at some point later. And as a reminder, we do also have a gaming YouTube channel at Obi-Wan Pez. Oops, that was not what I wanted. I'm on the wrong keyboard. So at Obi-Wan Pez and at N-Simplex Pachinko 6542 for those of you who are not actually watching this on YouTube. I guess you have to be on Twitch anyway. Okay, number 33. Let A and B be real numbers. Nope. Positive real numbers. The region in the second quadrant bounded by the graphs of y equals ax squared and y equals negative bx. Is revolved about the x-axis. Which of the following relationships between A and B would imply that the volume of this solid is a constant independent of A and B. So could it be that b to the fourth is equal to 2a to the fifth, or b to the third is equal to 2a to the fifth, or b to the fifth is equal to 2a to the third, b to the fourth is equal to 2a squared, or b squared is equal to 2a cubed. So if we're doing it for real, we're saying that we have in the second quadrant ax squared being a positive number and negative bx, again negative b being a negative number, but right. I mean, the easy one would be if the volume were to be 0, but can't necessarily use that one so easily. Okay, this is being revolved about the x-axis. So what we're going to do is to build our infinitesimal that we're going to use. So this is going to be dx here. This is going to be, if we let this be y1 and that be y2, and this is going to be y2 minus y1 is the height. So the individual areas are going to be y2 minus y1 all multiplied by dx. However, volume of what's going to eventually end up being a washer, totally a washer, is going to end up being the volume of the cylinder that we have, which is going to be pi times r squared. R squared is going to be y2. And then we're going to subtract pi times the smaller cylinder that we get, which is going to be the interior cylinder, or pi times y1 squared. Right, and then that's going to be dx, because now we want the height. Right, so pi r squared height. It's going to get us this. So we're going to want the limit as n goes to infinity of the summation of all of our individual v sub i's as I goes from usually just 1, but whatever. It's all good. Up through n. And this ends up being exactly the same as our definition of integrals. So we have here going from a to b. In this case, b is going to be 0. And a is going to be whatever the intersection point is. Ah, I cannot use that a and b. Curses. F for final, I for initial. Can't use I. All right, x1, x2, I guess. It's all good. So yeah. Can't use y1 either because I just use that for a function. Man. Sure. We use capital I for intersection. And then x final, y final. Sure, why not? As it turns out, that's just 0, 0. Volume as a function of x dx. So then how do we do that? Our yi is going to be equal to when we set these things equal to each other. So when ax squared is equal to negative bx. Ax squared plus bx. So ax plus b times x is going to be equal to 0. So either x is 0, we knew that already, or ax plus b is equal to 0. This means that x is going to be negative b over a. This means we're going to get going from negative b over a to 0. We have our v function, which is pi on the outside, just for simplicity's sake. Y2 is negative bx parentheses squared minus y1 squared. Yeah, no, that's fine. Ax squared squared dx. Squared x squared minus a squared x to the fourth dx. Pi times the integral, and actually no, we're going to do the integral. Here we have b squared x to the third over 3 minus a squared x to the fifth over 5. Evaluated from negative b over a to 0 needs to be equal to this is b squared. Well, okay, so first of all, this is going to be 0 for the first term. We get a minus b squared negative b over a cubed over 3. Okay, minus, that's already a negative, so that's going to be a plus here. Nope, hang on. Minus 0 plus. A squared negative b over a to the fifth all over 5. That's going to be a positive there. So we have a negative and a negative. So that's going to be b to the fifth power over 3a plus, that is a negative a squared b to the fifth over 5 a to the fifth. Fifth over So in theory, if we had taken this and said, okay, let's take the volume function and taken a derivative of it, we'd want it to be equal to 0 because then it would never change over its entire life. So that's really what we want here. So we would be getting effectively our v of x back. So like pi times the quantity. y2 is going to be the negative bx squared minus pi's out ax squared equals 0. If we do that, now we get basically the same thing we've got over on the right, but hang on. Yeah, no. We need to taking the derivatives of those. Well, it's all going to be constant, so it's all 0, but that doesn't... That's not what I wanted. Okay, x sub I is a variable. Ah, gross. It's the other way around from... how we're expecting this. So... So this is going to be still the derivative of negative integral from 0 to x of v of x dx. It's going to be equal to 0. So then we say, how do we actually take the derivative, or how do we take the... whichever. It's negative v of x equals 0, so just v of x equals 0 should be the same value. Let x be equal to negative b over a, which is the intersection point, or the value of the x stuff. All right, let x be negative b over a, so therefore, x squared squared minus negative b of x parentheses squared is equal to 0 either way, right? Squaring stuff, moving to opposite sides of the equation, can still end up with all the same stuff. So a squared x to the fourth minus b squared x squared. So x squared. Never mind on that last one. Let's just do the rest of what we got up there, then be happy with it. This is going to be a squared b to the fourth over a to the fourth minus b squared squared is b to the fourth over a squared. That's okay. Well, I just right, this is just b to the fourth over a squared minus b to the fourth over a squared is equal to 0. So that's true, although that's not what I wanted. We did something. So over here, my problem is that I don't know what it's all equal to, right? It's just, it's like it's equal to the volume formula, so therefore this is just V. But it's not really what we want. Okay, let's just suppose for a minute that these are supposed to be equal if this is constant independent of A and B. What the hell was that? Right, so with this, we would need to, just for instance, multiply both top and bottom by 5a squared. And then here, both top and bottom by 3. So it's going to be 2. Nope, those don't combine. 5a squared b to the 5th minus 3b to the 5th over 5a to the 3rd. 50 a to the 3rd. It's equal to 0. All we care about is the numerator then. So this is going to end up being 3b to the 5th is equal to 5a to the 5th. Damn. B's are going to go away. That's not going to go well for what we've got here. All right, let's let that sit a minute. Region bounded by the graphs of y equals x squared and y equals 6 minus the absolute value of x. Is revolved about the y-axis. Alright, what is the volume of the generated solid? Right, revolved about the y-axis. What is the volume of that generated solid? So it's this bit here. And that bit here. When we do this, we can just focus on the first quadrant. The second's symmetric anyway, so whatever, it's fine. So we want rotated about the y-axis. This would be easier as a disk. That's a lie. It would require multiple integrations if we do it as a disk. If we do it as a shell, this will work better. So the way we do shells is we're taking an infinitesimal again dx, and again in this case the functions are slightly different, but the thing works just pretty much the same. So this is going to be 6 minus x without the absolute value because we're just doing quadrant 1 of this, right, minus x squared. Okay, so when we're making a shell, I'm going to be taking the area of an infinitesimally small shell that's going all the way around. So what we want to do is then, before we do the integral, come up with the usual formula that's going to help describe all this stuff. V sub I volume is going to be the circumference of this object going all the way around times the thickness dx. So 2 pi times the radius is going to be the x value. Right, 2 pi times x gets us the circumference of that particular point if we make a circle. Then we multiply it by its height, which is going to be the function 6 minus x squared. Then we multiply by our dx, or I guess in this case, right, it's going to be delta x sub I. And then we take the limit as n goes to infinity of the sum as I goes from 1 to n of, again, 2 pi x times the function 6 minus x squared times, that's still just delta x sub I. Right, so this gets us the integral by definition of integral from, in this case, it's going to be from 0 to 6. Because here we're going to have this capture all of this distance. All right, so 2 pi x times 6 minus x squared dx. X minus x squared minus x cubed. Dx. This is going to be 6x squared over 2, so 3x squared minus 1/3 x to the third minus new power is 4, so this is going to be 1/4 x to the 4 from 0 to 6. 0 is going to clean it out, so 6 is the only relevant one. 2 pi times 3 times 6 squared is 36 minus 1/3. It's 216 minus 1/4 times another 6 is going to be 1296. $324, 72, and that is 108. Well, that's negative. I don't like that very much. Oh, we're not going from 0 to 6. We're going from 0 to the intersection point. That was very silly. Okay, intersection between oops. Right, so intersection. Got 6, no, not 6x. 6 minus x is equal to x squared in order to get the same point. So it's x squared plus x minus 6 is equal to 0, which can be there for x plus 3, x minus 2. Given the premise that I was trying to solve here, we're just going to get 2. Okay, 2 pi times 3 times 2 squared is going to be 4. Minus 1/3 times 2 cubed is 8. Minus 1/4. 2 to the 4th is 16. So that's 8, which means that this third of 8 is going to be taken away. So it's 2/3 of 8 times 2 is 4/3 pi of 8, which is, no, not 20, 32 pi over 3. That is an answer. Good times. C 8 pi D and E 6 to 23rds times pi. So we said we got part A there. Okay. We're going to take a quick break here for 3 minutes, go downstairs, cycle that water, stretch your legs, do whatever you need to do. I'm going to open up the window here to get some cooler air in. And thank you very much, everybody, for coming. Hope to see you in 3 minutes, give or take. Thanks so much for coming. Righto. Welcome back. I have no idea if this is going to work, but sure, why not? Okay, so that's okay. It's alright. So, unfortunately my Tai Chi class has been canceled today because my instructor's dad is not doing so hot, so the dude's like 80 something, so can understand. So just try to get the blood flowing a bit, and we'll also do like some essentially like the form but in standing mode. It's like it's really not gonna work, but we're getting pretty close to, like, I hesitate to say the end, but parts where a lot of the rest of the form becomes kind of repetitive. So good news there. We're going to be getting toward the actual end of the form pretty quickly. Righto. So stand with our feet in a V, start from bear, and then we shift into the right hip, straighten out the leg, straighten out the feet. Tuck into the left hip, come across with an energy ball as we move the pivot on the right heel, shift weight, come this way. Yes. So left hand is up in a ward off, right hand is down in kind of a prepared guard, just in case we're going to need that either for hitting something or for blocking something. It comes up right here, shift in, and then turn on the ball of the foot, and switch hands into ward off right, into a rollback, press, push, shift the weight back, come in here, do a single whip, and then step out, turn all this, come back up, lift hands, come down, go into shoulder, tucked the right, come up, and white crane. And these go here. Strum the lute. Brush knee again. that. Where should I be standing for this? This one is actually this way. Okay. So then we come, this is here, tuck in, bring this across, trade hands. So now all the weight that was being put on this arm, in case somebody's like trying to grab our arm or something like that, we shift it all onto the left. Oh no. What do I do from there? Oh, that's just a push. Come back this way, turn, and instead of single whip, we come out into this prepared stance. Then we drop to the left. Not quite like that. Carry tiger to mountain. How do we do this? Yeah, no, that's right. Okay. And that becomes roll back, press, oops, roll back. Man. Switch up, roll back, press, push. This way, single whip. Now we're facing 45 this time. Here we come back. Here we come back. Bring both hands this way, and it comes across. Single, it's a strike like this, and then bring our hand back. It's going to come out like this. This is a repulsed monkey. Brings back. No, this hand stays out. This hand comes back. And then as this comes forward, we step straight back. This comes down and around. Pops out like that. And then once we get, usually, I think we do one more, so we end up this way again. Yeah, so we end up this way again. You have to trade our hands around. Trade our hands around, and then we step real deep onto this side, facing out the other direction. And this is, we come out, bring the hands kind of together, and then, oops, come out, bring the hands sort of together, and then end up like this, with our right foot pointed at a 45-degree angle, and in front of our left, which is going to be facing straight out in the room. Then tuck here, come into energy ball again, and then as we come through, we do cloud hands, move the left foot this way, come across, bring the right foot up, do energy, or do cloud hands this way, do cloud hands this way, and then slip, step, energy, or cloud hands, and we keep going basically out like this, then out like that, then out like this, then out like that. And as we keep moving across the room, it's always a left hand in a ward off, right hand down, and we take a step, and then we come across, and then trade, step together, yep. Going this way, we come out this way, step, out that way, step, come across. And eventually when we get to here, we're going to take a step forward into the same sort of ward off prepared stance here. Then, this is the weird one. What happens is we go into the right hip and drop this hand in to like this kind of single whip sort of thing. Curl in, and then we are going to strike out like that. This is, like I said, this is the weird one. Strike out this way with a single whip. And then we duck down and like grab, basically you're grabbing somebody's calf, like around their ankle. And then stepping up and coming through with your elbow and your knee up like that. I don't remember what's happening with that one. And then you come back, and then there's a bunch more stuff, but that is as far as we learned a week and a half ago. So it's actually pretty good considering. Most of the time I forget stuff real quick. We're going to give ourselves a little bit of a bonus here. One of the last cream eggs in existence over here. White chocolate. Hashtag not sponsored. So yeah, I'm actually kind of surprised that we could more or less do the form in this tiny, tiny, tiny space. Sort of worked. Not quite, but, you know. Okay. Question 35. Calculate the length of the portion of the hypocuboid. Nope. Nope. Hypocycloid, which makes much more sense. So hypocycloid is something that's going to look more like this if we were to continue it on. A cycloid is the one that if you were to hook it onto like a light onto the outside of a wheel, the path that it would eventually follow would look something like this. On the other hand, if you affix something to the inner section of the wheel as it's moving, it would essentially look more like this. It would go a little lower. It would go probably not that far looped, but yeah, it's fine. Whatever. I'm exaggerating it. And then there's also a the other I forget the name. I forget the name of each of them, but there's the one where you affix something on the inside of the wheel away from the edge, and then there's something that if you were to extend it beyond the wheel. So, for instance, a wheel of a train usually has an extra height that goes beyond the rail. So you have like the normal wheel that's affixed, well, not affixed, but it is rolling along the top of the rail, and then you also have this bit that kind of scoops on underneath it. Of the hypocycloid, defined by x to the 2/3 plus y to the 2/3 is equal to 1. In the first quadrant, from the point 1/8 3√3/8 to the point 1, 0. Right, so in this particular case, we're looking for arc length. And typically, fx squared think that's how we usually run it. So if we were to attempt if we were to attempt this, this is also only going to work with rectangular. And you notice that this does have to be a function of x. So if this thing ends up looping back on itself, this is not going to work. We're not going to be able to do this at all. So one thing we can do is check Desmos real quick and just graph it. X to the 2/3 plus y to the 2/3 equals 1. Yeah. Okay, so the good news is this is just going to be, I can't actually grab it. We're just going to be going from, wait one sec, what was it? 1/8, so half, quarter, eighth. Well, we could just plug it in literally. So 1/8, comma, 3 square root 3 over 8. Nice. That's fine. Turn the label on and make it chunky, just so you can see it better. Up to 1/0, right? So that's easy enough. Drag. Oh, okay. All right, so we're going from here down the curve to here, 1, 0. So in this particular case, we are able to use a functional version of this. So y is going to be equal to 1 minus x to the 2/3, parentheses, raised to the 3/2. And yes, it will have a plus or minus or absolute value around the y, but we only care about the first quadrant. So we are only going to work with the positive here. Okay, so then x is going to go from 1/8 to 1. Just as that. So reminder on arc length, again, when you're working with rectangular coordinates, we were looking at some curve like this, and then infinitesimally, we want to look at what's going to happen when we draw a line. Oops. Alright, this is going to be dy, this is going to be dx. If we're talking about an infinitesimal or infinitesimally small amount. If we're talking about something that is, at least finitely large, we do have to generally put in this delta instead of d, but yeah, no. So here we're looking for the arc length s sub I for any individual length. S sub I squared is going to be equal to delta x squared plus delta y squared. Each technically with their own sub i's, but you get the idea. No, actually we do need those. Okay. So each of them individually gets squared, and we're just doing a regular Pythagorean theorem with this because our x and y coordinates are orthogonal to each other. They make right angles. Yeah, easy enough. Right? So any individual infinitesimally small arc length is going to essentially be just a hypotenuse of a right triangle. So then that means that s sub I is going to be equal to the square root of delta x sub I squared plus delta y sub I squared. But then we can also say that, hey, if we take a delta x sub I parentheses squared out from these terms because we don't have a delta x on the outside, which we really need, then this is going to end up with a 1 plus delta y sub I divided by delta x sub I parentheses squared. And then as we sum these up, we take I going from 1 to n, take the limit as n goes to infinity, so we have an infinite number of these little tiny infinitesimal arc lengths, and then we take the s sub I, and this is the, no surprise again, the definition of integral. So this is going to be the integral from a to b of square root 1 plus delta y sub I over delta x sub I is, oh, you know what? I messed up. That should not be f of x squared over here. This should be f prime of x squared. But tricky because nobody else is here. All right, then times dx on the end. So now we need to know what y prime is. It's going to be 3 halves times 1 minus x to the 2/3 raised to the 1/2 multiplied by the derivative of the inside is going to be a negative 2/3 x raised to the negative 1/3 power. So y prime is equal to, here we've got a 2/3 times a 3/2, so we're just going to get a negative x to the negative 1/3 times the quantity 1 minus x to the 2/3 all raised to the 1/2, well, not all, but 1 minus x to the 2/3 is all being raised to the 1/2 power. Okay, so for this, what's going to happen is we've got integral going from 1/8 to 1 of the square root of 1 plus parentheses. This stuff squared is going to be negative ends up getting squared, just becomes positive. X to the negative 1/3 becomes x to the negative 2/3 times the quantity 1 minus x to the 2/3 time, or raised to the 1/2 power when it gets squared is just going to be a 1. And then dx on the end. So 1/8 to 1 square root of 1 plus, that is an x to the negative 2/3. Because the exponent is now a 1, we're allowed to filter in, or distribute in the rest of the stuff. Okay, and then minus x to the negative 2/3 times x to the 2/3 is going to be 1. Dx. Anybody see the writing on the wall yet? Right, 1/8 to 1 square root of 1 minus 1 ends up just being 0, and we've got x to the negative 2/3 inside that square root dx. That's going to make it 1/8 to 1 of square root of x to the negative 2/3 is going to be x to the negative 1/3. When we take the integral, this is going to become x to the positive 2/3 multiplied by the reciprocal of the new exponent, so 3/2. Taken from 1/8 to 1. So 3/2 times 1 to the 2/3 is still just that, minus 1/8 to the 2/3 is going to be 1/2 squared, so 1/4. So 3/2 times 3/4 is going to be 9/8. Is that an answer? It is an answer. So that's positive at least. AO. Nine eighths. 3 root 2 on 4. 1/4 5 root 2 over 8, root 3 over 2. Again, we got 9/8. $36. What value of a belonging to the positive reals satisfies the following? Integral from e to the a to the e of dx over x times the integral from a to ax of dy over y. Is equal to 1. So if we start from the inside, right, the rest of the stuff looks too weird at the moment to deal with, so we just kind of move through and see what happens. So dy over y is going to get us the natural log of y evaluated from a to ax. Okay, natural log of ax minus natural log of a. Dx over x times natural log ax over, nope, natural log ax minus natural log a is going to be the natural log of ax on a. So those are gone. We're just left with the natural log of x. So we want to know what is the dx over x natural log x equals 1. Right. So this one, I think, is going to work very nicely with integration by parts. So we let 1 over x be v prime, and natural log x be u. So u prime is going to be equal to 1 over x dx. And then v is going to be equal to, here we're taking the integral of 1 over x. That's going to get us another natural log, though. Might be okay. We'll see. Alright, so a to the e. This is going to be hang on. But that's not in the same place, right? Right, that's not going to work. Oh, no. We don't need to let that all... Okay, that's... Never mind. Let u be equal to natural log x, u prime equal to 1 over x dx. Or du. So then this is going to be the integral of du over u, subject to those conditions up there where these limits are x equals, not u, which we could go through and change all these if we want to. That's perfectly fine. So if u is equal to natural log x, then x is equal to e to the u. No, don't need that. Integral of du over u is going to be the natural log of u, which again, x equals e to a to the e equals 1. Then transfer back. So instead, natural log of u is going to be the natural log of x. Evaluated from e to a to the e equals 1. Okay. It's going to be the natural log of a to the e minus natural log of e. All of that needs to be equal to 1. So how do we get how do we get a to do that? Here, this is going to be the natural log of e times, parentheses, e times natural log a minus natural log of the natural log of e is just 1. Natural log of 1 is just 0. With that multiplication, we can split it over a log and make this the natural log of e plus natural log of a is equal to 1. Natural log of e is 1. So we could subtract 1 from both sides, leaving natural log of a is equal to 0. And then raise e to both of those sides. We get e to the natural log ends up, I don't usually cross out like that, but effectively it does the same. So we're going to eliminate that particular term. We're just left with the natural log of a equals e to the 0 is going to be 1. And again, this is going to say that this is just A, and then this is just E on that side. Megalomorph! I mean... very true, I'm sure. And they've only been around for like 400 years, so... Okay. Let's see. A. 1 over E. B. Eth root of E. That's a fun one. C. Root E. D. E. And E. E squared. Yeah, zero's only been around for 1500. It's true. Okay. And we got D. The value of A should just be E. So that we end up with the initial question. We're going to take the integral from E to e to the E of, what was it, dx over x times integral of what was it? Oh no. Integral from a to ax of dy over y. Equals 1. Oh, okay. Those also need to be replaced in here. No longer a's, those are now e's. From e to ex. Well, as my students would be prone to saying, why do we even have to learn that? Because it's not about that one problem. It's about being able to recognize problems and then solving them. Cosine of x, all raised to the cotangent squared of x. Okay. So as x goes to 0, do a direct plug-in or a verification that this is not in fact going to work. So this is going to be the cosine of 0. Nope. Bracket raised to the cotangent squared of 0. And if we remember, cotangent of theta is equal to the cosine of theta over the sine of theta. And cosine at 0 is going to be 1. So this is going to go to 1 as right, 0 over 0. Oops. No, that's not. Okay. No, that's not a 0. That's a 1. Jeez. I'm okay. right? Which is going to infinity. We don't technically know whether it's positive or negative infinity, but it's fine. 37, evaluate. Half 1 over root e over 2, 1, and root e. Okay, we don't have an answer for that yet, but that's okay. So 1 raised to the 1 over 0, or 1 raised to the infinity, is indeterminate. Okay, so since this is indeterminate, we're allowed to use L'Hopital's rule. However, this in an exponential form is going to be really weird. So we take the limit as x goes to 0 of cosine x raised to the cotangent squared of x, and then we say, well, if this is going to be a limit L, then we can make this a bit easier by saying, let's take the natural log of the cosine at x raised to the cotangent squared of x, but that's a exponent now, so we can drop that up front as a multiplier. So cotangent squared x times natural log of cosine of x. We want to take the limit as x goes to 0 still. This is going to be equal to the natural log of L. We still want to figure out what L is, but we're just going to take a bit longer to get there. Okay, so again, cotangent is going to infinity, and our cosine is going to 1, which makes the natural log go to 0. So this is now infinity times 0. And yes, of course it's indeterminate. We already established that that was going to be the case for a bit. Okay, and then we could also instead make this a tangent squared at the bottom. And the natural log of the cosine of x is going to be there, equal to natural log of x. We're taking the limit as x goes to 0. All right, the tangent in the denominator is now going to be a 0, so now it's 0 over 0. Now it's a familiar indeterminate form. Not that it's any better necessarily, but we just know that from here we could also use L'Hopital's rule directly. right? So indeterminate of equivalent forms to 0 over 0. So yeah, we could actually technically do it all the way back up there with the cosine with this power. Don't know how you'd exactly go about doing it, but you know what? It's fine because we don't have a clear top and bottom. In this case, we have a clear top of the fraction, clear bottom of the fraction. So we're going to take L'Hopital's rule, which says we're allowed to take the derivative of the top and bottom separately and treat the limits as the same. So this is the limit as x approaches 0 of right, so the derivative of the natural log is 1 over the function times, this is now a chain rule, so the derivative of the cosine is going to be a negative sine of x. Yeah, we're not really getting anything else out of there, so that's fine. And again, this is equal to the natural log of what we actually want, L. And then the denominator is going to be, take the derivative of tangent squared of x is going to be 2. Nope. 2 tangent of x times the derivative of a tangent is a secant squared. Negative sine x over cosine x. Oh, hey, would you look at that? That is a tangent. Right, and then the denominator also has a secant squared of x. It's going to be a negative. Secant squared in the denominator is a cosine squared up top. Right, so now x is going to go to 0. We can now directly plug in. X going to 0 of cosine of x is going to be 1. So this is a negative 1 over 2 is equal to the natural log of L. Take e to the negative 1/2 is going to be equal to L. And that is what we're looking for. So e to the negative 1/2. 1 over square root of e. Okay, last one on this page, 38. We will do that just after. Now, you know what? We'll speed run this one, hopefully. 38. Let n be a number for which improper integral going from e to infinity of dx over x natural log of x bracket to the n converges. Determine the value of the integral. Okay. So this is going to be the limit as a to b, so b goes to infinity, of integral as x goes from e to b of dx over x times natural log of x to the n. This is also going to be the same as above. So u is going to be equal to natural log of x. Du is going to be equal to 1 over x dx. So it's all here. It's just a simple substitution. We could work on all that, or we could instead just say, okay, look, I know what it is. We're going to get a dx e to b, limit b goes to infinity, x, wait, that's not what I want. This is going to be 1 over natural log of x raised to the n minus 1, because when we do integrals, we're going from a particular power to 1 plus that power. But since we're on the bottom, right, we're going to be adding 1 to what's already a negative number. So it's going to be effectively 1 minus n. But here we can switch it down to the denominator and make it n minus 1. All right, so we do know that n needs to be greater than 1 for any of this to work in the first place. Okay, then this is going to go from e to b. Then also, we need to divide by the new power, which is going to be 1 minus n. Remember that the whole power itself really should be up in the numerator, not in the denominator, but we'll worry about that later. Okay, so now this is going to be limit b goes to infinity, 1 over 1 minus b times the natural log of x raised to b minus 1 minus 1 over, wait, no, it's x that's going to be replaced, not n. Jeez. Natural log of b, n minus 1 and 1 minus n, those places. Okay, then when we plug in e, we get 1 minus n times natural log of e raised to the m minus 1 right? Natural log of e is just going to be 1 raised to any power. It doesn't matter. It's still just going to be 1. And then we get the negative 1 over 1 minus n. Right, natural log of b as b goes to infinity is going to go itself to infinity. However, this then means that the denominator is going to go to infinity. Which means that overall, the whole fraction is going to go to 0. Then the and that means that this whole fraction here ends up going to negative 1 over 1 minus n, or 1 over n minus 1. That is an answer. So I do enjoy seeing that the thing that I think it is there. Okay, A is 1 over n plus 1, B is 1 over n, C is 1 over n minus 1, D is natural log n over n plus 1, and E is natural log n over n minus 1. I said C. My spouse said A. So that's fun. Yeah, yep. She missed the fact that n is in the denominator, so when you flip it back up to the top, it should be negative. All right. We're going to rate out. Thank you, everybody, for hanging out, having a good time tonight. We'll figure out who's here, who's on. We got Shark Geek. Started about 20 minutes ago. Belint is playing Saros. Got a lot of people on. Casey Snow Art is doing a sculpting of a winged serpent. Dr. Danny Anduza is doing more fossil science news. Rhacodactylus doing more pseudoscience and autism. Well, doing that. Let's go see Shark Geek. Hope you all have a good rest of your night. We'll be back tomorrow for TTRPG prep, and we'll see you hopefully then, or Friday for games. My name's Obi-Wan Pez. This is N Simplex Pachinko. Catch you later.